In this lesson, we will discuss manual operation of the primary flight controls. The movement of the flying control surfaces, in response to the movement of the cockpit controls, may be achieved manually on smaller aircraft. In a manual system, the control surfaces are connected directly to the cockpit controls by a system of cables, rods, levers and chains. Most manual control systems use flexible wire cables to transmit the movement from the pilot's control to the control surface. Cables have a number of advantages over push-pull rod type linkages. They have a very good strength-to-weight ratio. They are easy to route through the aircraft. Their direction can be easily changed using pulleys. Because of their flexibility, they are resistant to impact damage, and they take up less room and have less joints than systems using solid rods. In this graphic, we examine the manual control of the elevator on a light aircraft. The control of the rudder and ailerons is achieved in a similar manner using similar components. As cables can only operate in tension, the control surface is connected to the input control by two cables. The system is very simple in its operation. The pilot operates his control. It is connected by a push-pull rod to a lever arm which drives the cables. They in turn rotate another lever arm at the flight control end of the system. This moves another push-pull rod which operates the flight control. Pulley wheels are used where direction changes are required. In order to move the control, the pilot has to overcome the aerodynamic load or stick force. If he releases the control, this force will drive the control surface and the control back to neutral. Manual flight controls are therefore known as reversible controls. You will see in another lesson that powered flying controls are irreversible or non-reversible. The amount of movement of the control surface to either side of its neutral position is laid down, so that the required control can be achieved over the full range of operating conditions. The movement is not necessarily the same each side of neutral. For example, an elevator may have more control deflection upwards than downwards. The limit of movement of the control surface is determined by a mechanical stop. The function of mechanical stops is to prevent excessive control surface deflection, which may cause the aircraft structure to be overstressed during normal operations. The stop which limits the movement of the control surface is called a primary stop. A stop which limits the movement of the control column or rudder pedals is known as a secondary stop. When the control surface reaches the primary stop, there will be a small clearance at the secondary stop. If the pilot should apply excessive force to the controls, the secondary stops will prevent him from damaging the control linkages. A fair lead is a guide, manufactured from a soft metal or plastic, used where the control cable passes through the airframe structure, so that if the cable were to flex laterally, it would come into contact with the fair lead rather than the airframe structure. It is important to have the correct tension in the control cables. If the tension is too low, the cables will be loose, permitting excessive cable movement, and if the tension is too high, the controls will be too stiff to move. Cable tension is adjusted by means of turnbuckles. Here we show a typical turnbuckle. It consists of a central barrel and two end fittings screwed into the barrel, one with a right-hand thread and the other with a left-hand thread. The cable is attached to the end fittings. The cable tension is adjusted by rotating the central barrel, causing the end fittings to screw either into or out of it. Sufficient screw thread must be engaged between the end fittings and the central barrel of the turnbuckle to take the load which will be placed on the cable. To enable this to be checked, inspection holes are provided in the turnbuckle. To be in a safe condition, or in safety, the inspection holes must be completely blocked by the threads of the end fittings. This is verified by attempting to pass a hardened pin through the inspection hole. Once the correct tension is set, the turnbuckle is locked using locking wire or some other suitable device to prevent it vibrating loose. Changes of temperature will change the length of the cables, and also the dimensions of the airframe structure, but as they are made of different materials, the rate of expansion will be different. This will cause a change in cable tension. On some aircraft, a temperature compensator is fitted in the control system. This automatically maintains the correct tension if the temperature changes. In the temperature compensator in this graphic, the cables from the pilot's control are fastened to the two quadrants. The quadrants are free to rotate independently about the central pivot point. However, they are connected together by a strong spring in the damper unit. Movement of the pilot's control operates the cables. They rotate the quadrants equally, moving the push-pull rod and the control surface. If there is an increase in cable tension due to temperature change, then the cable tension will overcome the spring and rotate both quadrants as shown, reducing the tension back to the correct level. Similarly, if the tension reduces below the correct level, then the springs will push the quadrants in the opposite direction, again correcting the tension. Control systems should be free of backlash. Backlash is free or ineffective movement of the cockpit control when the direction of movement is reversed. It may indicate worn or incorrectly adjusted components in the control system. Excessive backlash can exacerbate the problem of control surface flutter. As you can see in the extreme example shown here, the column has to be moved a considerable distance before there is any reaction from the flight control surface. When an aircraft is parked in the open, strong or gusty winds could blow the controls against their stops with sufficient force to cause mechanical damage. To prevent this occurring, control locks are fitted. These may be external or internal, and may be fitted to the control surface or to the cockpit control. If they are fitted to the cockpit control, they may be arranged so that it is impossible to open the throttle until the control locks are removed. External locks have high visibility flags fitted. Obviously, all locks must be removed before flight. That is the end of the lesson on manually operated flying controls. You now know the advantages that cable control has over other systems. You should understand the purpose and function of the mechanical stops, pulley wheels, and fair leads. You should also understand what is meant when we describe a manual system as being reversible. Finally, you should understand the purpose of turnbuckles and temperature compensators.